should get, I'm setting up the YouTube right now. So just take a minute. Here they come. I don't know if we can hear them. Okay. Okay. So we are good to go on YouTube. Let me mute. I think I can get rid of that. Okay. And that. And that. All right. So another minute and I'll let them in. And then again at 12 noon, I'll ask the team that's doing the formal introduction to take over. And then you'll be ready to go after that. So. Okay, so we are live streaming on YouTube for the benefit of the.
Dr. Ice, you're muted.
You're muted.
Yeah, you're muted.
I got it. Okay, sorry. We're live streaming on YouTube for the benefit of the SSP family around the world. And we are recording, so please make sure your screen name is set appropriately. First name, last initial only. And we'll get started here in just a few minutes. Okay, so in the chat, you should see the link for the doc to put your questions throughout the presentation. Unless I believe we're going to have the presentation first and save most of the questions for the end. So type it in there real fast when you think of one. All right, and here in just a minute, our team that is going to do the introduction will start us off. We're almost all here. Okay, team 2 that has introduction, correct?
It's
I'm
team
sorry,
10.
10, I apologize, I knew that. All right, if y'all want to go ahead.
All right, so hi everyone. Today my team and I have the pleasure of introducing Dr. Bagenal, who will be speaking to us today. Dr. Bagenal is a professor of astrophysical and planetary sciences at the University of Colorado Boulder and a researcher in the fields of space plasmas and planetary magnetospheres. She was elected to the National Academy of Sciences in 2021, a legacy fellow of the American Astronomical Society in 2020, and a fellow of the American Geophysical Union in 2006.
Born and raised in England, Dr. Bagenal studied physics and geophysics at the University of Lancaster. She then moved to the US in the late 1970s to pursue her graduate studies at MIT, producing her 1981 PhD on data from the Voyager plasma science experiment. After 5 years back in England conducting postdoctoral research with Imperial College's Space Physics Group, she then returned to the US and joined the faculty at the University of Colorado Boulder in 1989.
Dr. Bagenal has also taken on a variety of planetary science missions throughout her career as an astrophysicist, where she primarily has had the role of a plasma scientist in the science team. And some of her missions include the Voyager Plasma Science Experiment, Galileo, Deep Space One, the New Horizons mission to Pluto, and her most recent mission, the Juno mission to Jupiter, which is scheduled to end this summer in July. And without further ado, we will now hand the stage over to Dr. Bagenal.
Well, thank you so much. Lovely introduction. I'm very honored. Let me share my screen and we will start discussion about Pluto. So I want to talk about the New Horizons mission to Pluto and how we all got started and what we found and how it's continued on beyond Pluto. So we need to go back, in fact, 30 years to the discovery of Pluto. And so, as you know, Pluto has an eccentric orbit. It's not circular around the sun. It orbits the sun every 248 years. And it was first discovered back in 1930, so 31 years ago. And it's not gone halfway around the sun since. So we're going to be talking about the flyby that happened in here and how we started thinking about the mission around the time of its closest approach to the sun, perihelion, 1989. So let's, oh, and very important fact, we'll keep coming back to this, that the second Kuiper belt object was discovered in 1992. That was a very important factor. So Pluto was discovered by a summer student, just like you, working, in this case, at an observatory over the summer. And Clyde Tombaugh spent the nights at the telescope, taking pictures on photographic plates and then spending the days looking at these plates to see if he could see an object moving relative to the stars. And indeed, you can see here the arrows point out this object that has moved relative to the stars. And that's the detection of Pluto. And then in 1978, there was a detection of Pluto's moon. Now, this very fuzzy picture that was taken, again, with taking a photograph through a telescope, you can maybe see there's a bit of a bulge. And that bulge seemed to change with a period, a steady period. And this turned out to be the moon, Charon. Now, with modern technology, we can do this a lot easier. We can detect objects using digital technology. And indeed, as I said, second Kuiper belt object was discovered in 1992. This is an important factor. And since then, we have made measurements of thousands of Kuiper Belt objects. So just to give you a sense of this, starting with 1989, this is a movie animation showing you the detection of objects. And you can sort of see these lines radiating outwards. It's because the telescopes at Earth are looking out in that direction and seeing a bunch of Kuiper Belt objects. But you can see there are many of them, some really quite large. Pluto is the big one down here. And but what's interesting is if you take the location of these and you tilt the solar system on its side and look sideways, you can see they're actually scattered quite a lot out of the ecliptic plane, the plane of the orbits of the planets. So these are many of the Kuiper Belt objects that have been discovered since this development of digital technology. So here's an example of many of them, very varied, different sizes, different shapes. Pluto is indeed the largest of them. And some of them are quite dark, some of them are very bright. Their surfaces have been affected by the environment in which they're sitting. We can talk about that later. Here are some examples of the larger ones. Several of them have moons, like Pluto. And then what's interesting is to compare them with the largest object in the solar system series that was observed by a NASA mission. Here's the latest sort of best picture we've got of Ceres. So when we look at Pluto and Charon, this is the sort of relative size and relative distance. So this is to scale. And now we put the Earth in there on the same scale. You can see how small they are relative to the Earth, but you get a sense of their size and scale. And then when it comes to mass, considerably less massive than the Earth. But what's interesting is that Pluto and moon Charon are the largest, it's the largest moon relative to the size of the planet. So it's almost a binary system. You can think of it that way. Now, this was the best we could do from Hubble Space Telescope. So from Earth, we're so far away, we really can't see very much. And here, there's dark patches, pale patches, but really you can't see much else. We knew the temperature. We can measure the temperature using measuring the heat coming off in microwave wavelengths. And the temperature is 40 Kelvin, minus 233 Celsius, minus 390 Fahrenheit. I don't care what units you use, it's darn cold. Now, the density tells you that it's pretty much half rock, half ice. And so we can measure this without getting up close. These were things we knew before we started campaigning to go to Pluto. So go back 32 years to 1989. I first started teaching, this is me on the top left, teaching an early class on solar system exploration. We just had the Voyager flyby of Neptune, and I was advocating that after Voyager, we should send a spacecraft out to Pluto. There was a young graduate student, Alan Stern at CU, and he was very keen to go to Pluto and persuaded me that we should work together to do this. And so we started campaigning to NASA. And there were several mission studies that happened. And the first few, really went nowhere. But you'll see in the middle of this sequence, around 1992, remember that date? That's the year when we discovered the second Kuiper Belt object. And since then, many more. So as more Kuiper Belt objects were being discovered, it became clear Pluto was not on its own, not a rare exception, but was one of many. And so the case to go to Pluto became a lot stronger. And in 2001, we won a competition with NASA, and the mission was selected to go, New Horizons mission to Pluto. So we had to write a proposal. We had to advocate to NASA to go. See, all dressed up in our suits, looking our best to advocate to NASA. We won the proposal, then we had to start building the spacecraft. Here is the spacecraft, bottom left, being built at the Applied Physics Lab in Maryland. And you can see the antenna, the radioisotope thermoelectric generator is on the side. You have to test it, you have to spin it, you have to shake it to give it a sense that it's going to survive in space. And then we get ready to send it off. Now, let me go through the instruments that we've got on board. We've got a couple of, we use the radio antenna to here to actually measure the motion of the spacecraft very carefully. And we can measure aspects of the atmosphere using the radio antenna. We have charged particle measurements, SWAP and PEPSI. And then we have cameras, a long range camera, Laurie. Ralph is a wide angle color camera, and Alice is the UV camera. And then the most important instrument of all is the student dust detector that's on the back. So this was designed, built, tested, operate, and the data analyzed by students here at the University of Colorado in Boulder. And here are some of them on the top left. These are all moved on to be mostly professional aerospace engineers or scientists in the space business. And they built this instrument, which you see down here. And what it is, it's about the size of a dinner tray, you know, or a lunch tray. And it's got pieces of plastic, and those pieces of plastic are very special. When a piece of dust hits one of these pieces of plastic, it gets counted. It makes an electronic pulse, which is counted, and the data is sent back. So remember, it's on the spacecraft. The spacecraft is moving at something like 20 kilometers a second or 30,000 miles an hour, that sort of speed, and through the solar system, and it measures the dust as we go through the solar system. Now, if this was an open class, I could ask you this question. How many pieces of dust do you think it measures? Is it 1,000 counts a day? 20 million counts a week? Is it 1 count every month? Well, I'll tell you the answer. It's a few counts a week, not very many. And so that tells you that space is very empty. And as we're going through, it's not a case of having to be constantly hit by objects, which is sort of the Hollywood view of space. In reality, it's pretty empty and we don't hit a lot of dust. We do measure the dust, and it's important because that dust is made by the collision of material, collision of objects in the outer solar system. It tells us about the collision rate of objects, but it's not enough to damage the spacecraft. Okay, so eventually we have launch day, January 19th, 2006. We all go to Cape Canaveral. I'm with a student dust counter students, and we watch the launch. It was a very light spacecraft and a big launch vehicle, and we had a quick passage out through the solar system. We actually got a kick out at Jupiter to increase our speed out there. Now, in the meantime, just before we launched, Hubble Space Telescope had been looking at Pluto and Charon, and it had found 4 more objects, 4 moons, Hydra, Nix, Kerberos, and Styx, very small compared with Charon. So now we've got 6 objects to look at. So our whole system just got a whole lot more complicated. So I'd like to take a little time out to talk about why this is important. Why do we care about the Kuiper Belt? What's this got to do with our solar system and what's important about it? It's really about the issue of solar system formation. How did we get our solar system to be the way it is? And then hence us, Earth, and us in the solar system. So we start off with a young sun that is just this gas cloud that's out there in the universe, begins to collapse. And as it collapses, its gravity, it cools off, the gravity pulls the mass together. And as it collapses, it spins faster and faster. So a bit like a skater pulling in her arms, she spins faster and faster. Conservation of angular momentum. And so what you end up with is a disk of material that is spinning around. What you find is that you're close to the sun. It's going to be hotter. And so rocks and metals will begin to condense. And then as you move out, it gets colder and colder. And at some point at the frost line, ices will begin to condense as well. Now, there's a lot of ice in our universe. There's a lot of hydrogen and oxygen. So you make a lot of water that condenses to make large snowballs. And those large snowballs then become the centers of the gas giants, Jupiter, Saturn, Uranus, and Neptune. So they have cores of a large ice cores, and they have enough gravity. So once you get to be, in the case of Jupiter, about 20 Earth masses of ice, can have enough gravity to pull in the hydrogen to make the gas giants. Now, inside in the inner solar system, you've got rocky planets. They're smaller, there's much less rock in our universe, materials that make up rock closer to the sun. Now, the problem is, though, we've been discovering that it's really hard to make Uranus and Neptune where they are out in the outer solar system. And so there's been a new idea that said, okay, what if we make a simulation of a system that has Jupiter, Saturn, Uranus, and Neptune in close to the sun, closer about where they are now, where Jupiter is now, 5 times the distance between the Earth and the sun. And then we put a whole bunch of objects around it, icy objects, say, planetesimals, and then we run a numerical code that allows for gravity of the sun and the orbiting and the gravity of the giant planets to see what happens to those objects. So at first, not a whole lot happens. It takes quite a long time for there to be any changes. But at some point, a few 100 million years into this system, it begins to get a little unstable. And we see that there's a resonance between Jupiter, Saturn. Oh, there it went. And you can see what happens is you scatter all the objects, and Uranus and Neptune move out. We'll just run it again because it's kind of fun to see this. And so this simulation shows you that after a while, you get resonances between the orbits of Jupiter, Saturn, Uranus, and Neptune. It pushes out Uranus and Neptune to their sort of current orbits, and in the process scatters all these icy objects outwards and inwards. Now, this is important because this scatters these planetesimals throughout the solar system. It puts Uranus and Neptune in their right orbits, and it delivers water to the Earth. Because remember, if the stuff that was close to the sun is only rock and metals, we wouldn't have oceans, we wouldn't have life, we wouldn't have humans. And so we need to have, early in our solar system formation, water being delivered in. So the point is to go and find out at Pluto what Pluto is like, to understand the Kuiper belt, to test out these ideas of solar system formation. So we've launched in 2006. We have a 9.5-year journey, long time to get all the way out to Pluto, because Pluto is out beyond 30 AU. AU is the distance between the Earth and the sun, and so it's a long way out there. And moving at 33,000 miles an hour, we move through this system pretty fast. We go through the moon system, go behind Pluto. This all takes only 4 hours, okay? 9.5 years and 4 hours when we get there. But what's also interesting is that out of that distance, with radio transmission happening at the speed of light, the one-way communication time is 4.5 hours. So we can't control joystick this spacecraft. It's a robot. We have to tell it what to do. It does it, and then it turns back to Earth and tells us, yes, I got your data for you. So here's a simulation, gives you some sense. We make the spacecraft move around so we can take pictures of various things, the moons, the planet, and scan across the system. And then we take pictures for several days in advance as we're approaching. And then when we go past, noting that we're moving really pretty fast, we don't have a lot of time to take a whole lot of pictures. And so then as we go by, whoosh, we're on the other side, turn back and look towards the sun and take pictures from behind. So what do we do while we wait? Well, we took selfies. This is the team. This is the women on the team. It's about a quarter of the team. And we just thought it'd be fun to take a picture to show the variety of people involved in the mission. I'm over on the left, by the way, you can see me there. But what's interesting also is that finally, the mission operations manager, or MOM, as we call her, Alice Bowman, she announces that the spacecraft is well and full of data. And it is kind of interesting to see the difference between the Apollo astronauts landing on the moon and the celebrations at Mission Control. The Mission Control of 1969, smoking cigars, notice, compared with 2015. Things have changed. And we all went nuts. It was so much fun and so exciting after all those years planning for this mission to actually get some data coming back. And boy, were we lucky with the amazing pictures we took. The world, nobody really expected this incredible view that we got of this icy world with a heart. And so what we're looking at here is ice. We named them after a whole bunch of space missions and space fiction. Though, of course, we also had to name a region after Clyde Tombaugh, the discoverer of Pluto. So there's a mixture of science fiction and real spacecraft included in the names. Now, you only have a limited amount of time. The spin period of Pluto is 6.4 Earth days. And so we only really got high resolution pictures of one side because we're going by so fast. The other side was illuminated half an orbit later. And so we're much further away, so they're fuzzier. But we did get high resolution pictures of this side with Sputnik Planitia, the heart. So you can see here, this gives you a map, the areas that we get the best pictures versus the fuzzy pictures. But we got a pretty good map of the whole planet. The bottom half was actually at darkness. It wasn't all illuminated. Now, when we look at the ice, what we see is, and we can use the spectrometer, the colors, to get a sense of what the composition is that a lot of the whiter colored ice is the fresher ice, is nitrogen, CO2, and methane, CH4. And the water ice, H2O, is actually hard as rock, and it acts more like rock, and the mountains are made out of water ice. The nitrogen ice is much softer and can flow more easily. Now, when we look at the cross section, and we can get a sense from the gravity, the density of Pluto is a little under 2 grams per cc, so a little under twice that of water. So we think we've got about 1/3 ice and 2/3 rock. And you can see here that this means then the outer layer is about 300 kilometers of water ice above the rock. And there's some question that maybe the heat of the rock underneath may in fact have melted the underlayers. But don't think that's an ocean where we can go look for life, because 300 kilometers of water ice is a big thickness of ice. So when we look at the composition, what we see is that there's a big difference between the location of the water ice, which tends to be the older areas, we can tell because they're covered with impact craters. The fresher areas that look clean and white are, so the nitrogen ice, the methane, the CO2 ice. And then there seems to be some black stuff that is there. Where does this come from? Now let's just think about Sputnik Planum. That is, looks like an impact crater where maybe there was an oblique impact coming in at an angle. And so you end up not with a round impact crater, but this sort of oblong, this sort of stretched out crater. And this is filled up with nitrogen ice. We have some sense of the topography, the depth and height of the mountains around it. And this sort of suggests that this really is an oblique crater. We can also, it's actually similar in many ways to the Hellas region on Mars. Same sort of thing happening. Now, the ice that's in this Sputnik Planum seems to be flowing. Now, what's the evidence of that? Well, if you look around the edges, so remember this sort of mountainous region is actually water ice. You can actually see flowing here is the nitrogen ice flowing. But more important is if you look in here, you see what looks like cells here, okay? You can see these cells. And the idea is that these are in fact convection cells, a bit like if you have soup on the stove, you put heat underneath, it turns over and flows. Now, this is ice flowing, but it's quite soft ice. So it's a bit like semi-molten ice cream, if you like. And so you can see up here, these are the cells, and you get a sense that this is ice convecting. And the water ice is actually more rigid, but it also floats. It's less dense than the nitrogen ice. So you have these sort of icebergs of water ice floating in the nitrogen ice. Very bizarre, very different to what we experience here on the Earth. Here's an example of these mountains sort of sitting in the ice. And you can also see some sense of the snow, if you like, on the top layers being blown. It's almost like these are dunes of nitrogen ice being blown around. When we look at the craters, it seems like the edges of the craters, which stick up a bit, are where it's colder, and you have methane frost around the edges of the craters. Here you can see darker in the central region. We'll come back to that dark material in a minute. And then there are other areas where you see as the moon cooled off and contracted, there are these, you can see these cracks forming. So there's a real geology of a cracking crust. But remember, again, this is water ice that acts much like rock works on the Earth and other rocky planets. So this is water ice acting like rock, cracking up as the planet cools down. So here we have a simulation of the flyby. You can see the moons orbiting Pluto. We go fly past, we take a bunch of pictures, and then as we go past, we look back at the sun and see the sun passing behind Pluto. And what that tells us is about the atmosphere. We're able to look at the atmospheric structure and we see hazes. This is a real image taken of Pluto's atmosphere, the hazes in the atmosphere, looking back at the sun. The sun is behind Pluto here. Now, as the sun goes behind Pluto, we can use the UV instrument to measure the UV light from the sun. So you see here, these are the data. They start off quite high here, and then it drops off, but it drops off a long way from Pluto, and then suddenly plummets when we get in really close, and comes back up and then rises back on the other side. And so what we're seeing is a thick atmosphere here, where it's absorbing all the solar UV light, but a quite extended atmosphere, this outer atmosphere up here. And this is the atmosphere that is expanding, and a lot of it being lost out into space. Now, what's happening with the UV light interacting with the atmosphere? Remember, we have methane in the atmosphere, CH4. If you have UV light interacting with methane, you end up making larger molecules, ethane, acetylene, and even bigger molecules. And so we think that the brown stuff on the surface has been rained out. So in the lab, we can make these things. So you mix of nitrogen, methane, and CO2 in the lab, and you add UV light. You make these things called tholins. This is actually something that Carl Sagan was involved in doing in the lab. And these darker reddish objects, materials, substances, we think that what's causing the darkness on the surface. So these dark areas like Cthulhu region is probably has collected over millions of years this material that has rained out of the atmosphere, these hydrocarbons that have rained out of the atmosphere onto the surface. Whereas the fresh areas here are fresh, turned over ice that has removed the tholins, or the tholins are circulated inside. So here's an example where you can see the fresh material in Planum, and a really nice view of this site, turning over of material here, cells of convection here. But then when we look at the rock, which is in fact ice here, you've got the ice layers, you can sort of see there are layers of dark material interleaved, suggesting that you have deposit of the dark material, and then you have episodic changes, maybe more snow coming down and more ice forming, and so on. So we can see the geological strata in the ice associated with epochs of deposition of dark material, those hydrocarbons, and then fresh ice on top. Now, there are some other features that we see at Pluto that are completely different from anything else we've seen. In particular, there are these pits. Who knows what's going on here? Very bizarre. Maybe these are areas where more volatile material comes shooting out and makes these holes. We really don't have much of a clue what they are. Other places we see things that are similar to what we see at Earth, called sun cups or penitentes. We see these a lot in Colorado. This is where you have a whole load of snow, and then the sun heats up and material evaporates, and you start off with these sun cups on the right, and then eventually evolves to make these penitentes. But at Pluto, maybe these have evolved similar things that we're seeing at Pluto, but it's taken a million years to make large-scale features. There's another feature that no one really expects to see, which is kind of like a volcano. It looks like a volcano, right? It's quite large, 50 miles across, you can see from the bottom right. And it's in fact about 2 miles high. So this is a really big mountain. And it seems that material, maybe volatile material again, comes spewing out of the interior. And this is a little movie of this ice volcano. Really a lot of structure. Again, this is ice, looks like rock, but it's actually ice. And then maybe volatile material shooting out from below. This is totally unexpected. And we're really only just really beginning to understand what's going on here. Another strange kind of material are these ridges, which maybe could be made out of methane. These are quite large. It's not like this is sort of a little feature like those penitentes that we see on Earth that you could walk through. These are large structures, tens of hundreds of feet high, and really strange. And maybe this is methane ice that has been blown into form these structures. So very unusual morphologies of the geological features here on Pluto. And one of my favorite pictures is this overview taken as we're flying away. You can see the plains of Sputnik Planum on the right. This is the methane glacier, not the methane, the nitrogen glacier on the right with convecting ice underneath. And on the left, we have water ice forming mountains. And these mountains are as big as the Rocky Mountains here in Colorado and sticking up. And then you can see in the distance, the haze in the atmosphere, layers of haze. And this is the hydrocarbons precipitating out, sinking down and covering the surface. It's a beautiful view. Doesn't this look like a planet to you? Now, when we look at Charon, the moon, we see more geological features, it seems less active impact craters. We're not sure where this brown stuff comes from. Some people think it was actually blown from Pluto across, or maybe because Charon doesn't have much of an atmosphere, or maybe it is energetic particles bombarding the surface and changing the surface chemistry. There's a big question as to why Charon just has it in one region around its poles. Now, the other four moons are really bizarre. These are small, just little irregular lumps of ice and rock. But the funniest thing is that when we measure their rotation, we have Pluto and Charon, these brown things in close orbiting around each other in synchronous orbit. And then these other ones are spinning like crazy. Just look at Hydra. It spins nearly 90 times around in one orbit. Very bizarre. And so we don't know how they got to be this way and what is the physical process. So this is a topic, maybe you could get interested in this. Maybe this could be a project that you could work on and think about how it got to be this way, because we just don't know. So very bizarre. Okay, so after flying past Pluto, we then decided, what else do we do with New Horizons? It was just a flyby, keep going. Let's see where we could go next. Well, it turns out that with Hubble, we found a target to fly by without having to change the orbit. We only had enough fuel to change the orbit, the motion of Pluto going out from the sun by about 2 degrees. So if you hold your hand out, hold up 2 fingers, 2 degrees is about the width of 2 fingers, just a tiny motion of the spacecraft to target this object. It was called Kuiper Belt Object 2014, year it was discovered, MU69. That was just its name. And so after flying past Pluto in July of 2015, we targeted MU69 for January 1, 2019. So to give you a sense of the size, if Pluto is an exercise ball, then MU69 is just a ping pong ball or a golf ball, really small, right? So we're going from a fairly, the largest Kuiper Belt object, but it's still pretty small compared with, say, the Earth, and then a really small object out further out in the Kuiper Belt. So it gives us a sense of different objects. Now, before we flew by, we used a technique that is used for a lot of asteroids and a lot of Kuiper Belt objects, which is you have observers on the Earth with different telescopes looking out at an object, and they look at a star, okay, out here, and you have different observers looking at this object. And each of these observers measures a dip in sunlight, a starlight, a dip in starlight, a dip in starlight, each at different places across the Earth. And by having different sizes of these dips, these occultations, from that you can put together, when you're looking across the object, different sizes, different depths, you can work out the size of the object you're looking at, the size and shape of the object, okay? Because you're getting different cross sections by looking at the star moving behind the object, and the amount of dip in that starlight gives you some sense of the size and shape of the object. So this was done for our target, MU69, and we had all over the globe, these fairly small telescopes were used to look at the object to see if we could get a sense of its size and shape before we arrived there. And here is an example of a group that was out in Senegal trying to make observations. They had about 20 teams spread across. And the one team that was actually successful had one of my students, Parker Hinton. You can see he was pretty cold at night, and they were all dressed up. And he actually had the US ambassador helping him observe. And they used this telescope, and they were able to detect a signal as the star moved behind MU69, our target for New Horizons. And that helped us get a sense of the shape before we arrived there and get a sense of its location, because we really wanted to target this and go by properly. So we needed this support beforehand. Now, as New Horizons arrived, we could start making measurements of its shape. And the first observations, you can see you just get a few pixels, and then you sharpen this and you get better pictures as you get closer. So this was 37 hours before closest approach. So we were getting close. And then the day before, we made this measurement. You can see the size. It's just 21 miles across, or 33 kilometers in length. And you can see now it's got a funny shape. It's not round. What's happening? And then this, the next day, we get a sense of its real shape. So it's funny because it started off with this sort of name, MU69, and we wanted to give it a real name. And we started calling it Ultima Thule, but people were not very happy with that name. It didn't have good connotations. Other people just called it the snowman. And in the end, we named it Arrokoth, which is a name associated with an indigenous population in Maryland, which is where the spacecraft was built. So Arrokoth is its official name of the International Astronomical Union. So you can see it's a two-part object, okay? What we call a contact binary. So two pieces that came together and stuck. And looking at it with different wavelengths, different resolutions, you can see two pretty round objects. They seem to have some dimples with some impact craters, and it looks as if around the neck there's some fresh ice. So the idea is that you have two objects that come together. Now, you just, first view, people thought, oh, these are two round objects. They come and hit each other. And then we looked more carefully at the images and decided that actually they are more flattened. They're not actually round. And so the idea is that about 4.5 billion years ago, or just after the Uranus and Neptune migration that sent all this stuff out into the Kuiper belt, they bumped into each other, came together, the pieces of material bumped into each other, came together, and eventually rotated around due to gravity, orbiting each other, eventually left two objects which merged quite slowly. They probably moved quite slowly together. If they'd moved fast together, they would have broken up. So by looking at the way in which they'd come together, we think they probably were, it's sort of like walking pace. They would have bumped into each other pretty slowly. Okay, so now what have we got in store? We are still moving away from the sun. We're following the voyages out through the solar system. Currently at about 50 astronomical units. We're going to keep going. And we want to keep measuring the dust and the solar wind. So where does the edge of the dust drop off? Where's the edge of the Kuiper belt? We think it could be fairly soon that we'll see the end of the dust being generated in the Kuiper belt. And as we move outside the Kuiper belt, that dust will disappear, or maybe it won't. We don't know. We'll have to see. The solar wind moves out from the sun. The Voyager 1 and Voyager 2 have now moved outside into the interstellar medium. They've moved outside the sphere of influence of the sun, the heliosphere. They're out in the interstellar medium. And it'll take a while for Voyager to get there. May not survive all that long. It's moving slower than the Voyagers. But we will measure the solar wind in the outer. It's the only object, in fact, only spacecraft beyond Mars out in the heliosphere. So we want to measure the solar wind as we move out. But there's also a hope that we'll see another Kuiper belt. We're looking for candidates. We expect to be power, keep us going for a while. And with a bit of luck, in the next 5 years, maybe we'll fly past another Arrokoth, or something like it, or something completely different. So this mission has been quite amazing. When I started with Alan Stern campaigning for this mission to Pluto back in 1989, 32 years ago, I had no idea that we would come to an object that is so complex, full of exciting, icy geology, with all sorts of features, impact craters, mountains, glaciers, flowing ice layers, ice volcanoes, these weird pits on the surface, and then layers of the atmosphere with hydrocarbons raining out onto the surface to make this gooey, oily surface in places. So really phenomenal, exciting object with all sorts of interesting geology, telling us about these icy objects of the outer solar system that play an important role in our solar system. And with that, I will thank you very much. We had many people involved in this mission. This is just the science team. It takes a lot of people to send a spacecraft out into space. And I hope that you will be excited to have follow-on missions, all sorts of places to go in the Kuiper belt, all sorts of places to go in the outer solar system. I'm hoping we're going to go back to Uranus and Neptune very soon. Lots of fun things to do. And with that, I'll thank you very much. And I'm happy to take your questions. I will stop sharing. We can go back and look at some of the pictures if you want, but I understand that you are going to be asking me questions. So fire away.
Hello, Dr. Bagenal. So today my team is responsible for asking questions. Thank you so much for this interesting lecture, and I will start from the first one.
Okay.
So if you were to send a mission to the Pluto today, what what devices and detectors maybe would you equip it with?
Well, the most important thing is that if we go back to Pluto, you've got to find a way to go into orbit. I mean, a flyby is good, and we've done a lot with flybys. Voyager, after all, did flyby of Jupiter, Saturn, Uranus, and Neptune, got all sorts of fantastic first observations. But you want to follow up a flyby with an orbiter. But the problem with Pluto is that it is small. You can't use the gravity of Pluto very easily to get captured. So you're going to have to find a clever way to slow down so you can get captured into Pluto orbit. And I'm not sure we really know how to do that yet. So we would want to go into orbit. We would want to carry cameras, obviously. We would want with different wavelengths. We would want to, particularly to measure the composition of the ices in different regions. We would want to measure the atmosphere. Maybe we'd want to sample the atmosphere, flying through it with a mass spectrometer and measuring it. But I'm curious, what questions do you want to know about Pluto? What would you, other instruments that maybe you would want to carry?
So concerning the Pluto, so as you mentioned, there is a question. As you mentioned, Pluto consists mostly of ice. So the question asks, could Pluto be considered a large comet, and would it behave like a comet if it entered the inner solar system?
Well, in some ways, yes. It's actually 2/3 rock by mass and 1/3 ice. So it's a pretty rocky object compared with a comet. Comet is more like Arrokoth, okay? Much smaller, much smaller, and which is pretty much all ice. Now, if you were to take Pluto and bring it into the inner solar system, yes, the ice would evaporate and it would come off and it would become ionized. Absolutely, it would. But is it more like a comet, or would it be more like Mars and Venus, whose atmosphere gets stripped off by the solar wind? So somewhere between the two, I would say. So a very large comet or a very small Venus.
Thank you. Next question. So you mentioned the SDS, Student Dust Counter, which was one of the devices on the spacecraft. So what does the data collected from the SDS reveal about the formation of the solar system? Was there anything maybe connected to the concentration of dust in the asteroid belt, or anything else? Any interesting insights?
So the Student Dust Counter measured pretty much a constant dust rate going out through the solar system. It did not see a big increase in the asteroid belt, which is sort of interesting. That's telling you that the asteroids are no longer bumping into each other a whole lot, right? And what we're expecting is that as you go outside the Kuiper belt, the amount of dust is going to drop off. Now, where does the dust come from? Well, partly it's from Kuiper belt objects bumping into each other, but that happens fairly rarely. Everything's moving quite slowly in the outer solar system. The other source of dust is indeed comets, which come in from the Oort cloud way far out, come in as they come near the sun, they evaporate, send off material, including dust and gases. And so the question is, with the Student Dust Counter, which is the only instrument to measure dust beyond a bit beyond the orbit of Saturn, so all the way out beyond that, it's very important to be making those measurements. But it's telling us when we see the edge where it drops off in the outer solar system, will be telling us about where the comets begin to produce dust and where the edge of the Kuiper belt is in terms of generating dust. So it's one of the most important measurements that we want to make in the next 5 years is there a decrease in the dust rate as we move further out? You're trying to ask another question, Ivan, because you're muted.
Okay, before pressing the space button worked for me, but now it didn't. Never mind.
Such is life.
Technologies, I guess. So next question is, how has the development of computational and observational technology influenced the Pluto mission? How do you think it will affect future space missions?
It's extremely important. You know, the Voyagers were launched in 1977, and their technology comes from early 70s. I mean, they carried a magnetic tape for the storage. They we used, when I analyzed the data for my thesis, we used punch cards. I had to have a bunch sitting in my office, you know, so this is ancient technology for Voyager. By the time we get to New Horizons, of course, it's digital technology, but the capabilities when we built this, you know, around 2001, compared with now, is amazing, right? The storage of memory is enormous, and the capability of the onboard computers is huge. Now, there are various things that happen now with new spacecraft. They are robots. That is, you tell them what to do, they go do it, and then they come back and tell you what they found, okay? And that's very important. The increasing amount of autonomy that these spacecraft have is very important. They can go off and do things and decide how to move around or what to look at or focus in on something and so on and so forth. So new technology is key for getting lighter and lighter, getting more and more capable. And I think that when you start working on space missions, your generation will find that there's a lot more onboard data processing than there is now. It used to be we would just send it all back to Earth, collect it with the deep space network, the big antennas on the ground. All of the data would come in, and then you would analyze it. But it would limit the amount of data you could bring back, okay? And so I think new technology, you'll be doing a lot more on board and only sending the meaningful numbers back. So say you take a picture of the sky and it's mostly black with a few objects. You don't need to send all the black pixels back. You just send the non-black pixels back, okay? And so that will make a big difference, I think. Modern technology, computer capabilities will be huge, very important.
Thank you. Next question is, are there any other current or planned missions designed to explore the Kuiper belt?
The planetary science community is right now going through, every 10 years, we have a sort of planning session. And we're going through this decadal survey of planetary science and astrobiology, trying to decide what are the most important things to do next? Where do we want to go? And there are a variety of candidates. I think we should go back to Uranus and Neptune because we've only just done flybys. We don't really know what they're like. Very important gas giant objects to try and understand what they're made of and how they work. There's another push to go to Venus. I think Venus is extremely important. It's our sister planet, our neighbor, and we know so little about Venus, extremely little about Venus. It's got a runaway greenhouse atmosphere and very hot surface. It has lots of geology, all sorts of things, but we know extremely little about it. And I mentioned Venus not because I want that mission. It doesn't have a magnetic field, so I don't really care. It's because I think it's our neighbor, and we really should understand our neighbor. So there's a push to go to Venus. There's also a push to go to the Kuiper belt and understand the Kuiper belt. And there's a push, there's a competition between those that say, go back to Pluto, and others who say, let's go to a different object and compare it, maybe Eris, one of the other ones, and so on. I actually think we should go somewhere else and look at one of the other ones, but there are people who want to go back to Pluto. So there are pushes to do this, but again, as I mentioned before, we need to think about the technology of how to get there efficiently and slow down when we get there so we can maybe go into orbit. And that's a difficult technology that needs to be developed.
Next question concerns Planet 9, Planet X, so-called. Does the New Horizon attempt to detect Planet 9 in any way? And do you think personally that Planet 9 exists?
So my understanding of Planet 9 is that it's in the wrong direction for New Horizons to be able to detect anything. So we're not going to see anything there. I think the idea of there being larger planetary objects further beyond the Kuiper belt is a very interesting one. You saw that simulation I showed you of Uranus and Neptune being kicked out by Jupiter and Saturn, migrating out. One could imagine a situation whereby a Neptune-sized object gets kicked further out and goes into some eccentric orbit. I don't know. So it's possible. There's scientific arguments about whether you need to have another object much further out in order to make the Kuiper belt the way they are. And this is a sort of hot issue of debate amongst the dynamicists, people who study the dynamics of the Kuiper belt. So watch this space. We don't have the answers yet.
Yeah, next question concerns the second object the mission was flying by. I don't remember how it's called.
Arrokoth.
Arrokoth. Those two balls merged together, right?
Right. The snowman.
Yeah, snowman. So I'm wondering, so what is the physical process behind the creation of that neck from two objects orbiting around each other, and then the neck is created? How does it work?
So so say you have a bunch of stuff out there, right? A bunch of ice balls. They're all floating. There's a whole bunch of them, and two or three of them merge together. You get some bigger ones, and they start to form this. Once you get some mass there, gravity begins to take over, and they start orbiting each other, and then they start bumping into each other, and then you end up having two bigger pieces, and then they slowly begin to orbit each other, and then at some point they come together and keep orbiting. But they have where they touch, you sort of melt the ice, and they sort of then refreezes, and so you end up with the neck is sort of where the stuff's come together, melted a little bit and stuck. So it sort of acts a bit like glue sticking together, right?
Yeah, makes sense. Thank you. Next question. What is the most unforgettable challenge you had to overcome in your career, I think?
Oh boy, that's a difficult question. I think it's sort of having to stick with it when things get tough. That is, you're trying to debug some code. You're trying to analyze some data, and the answers just don't make sense. And you're frustrated that it doesn't make sense, and you don't understand, and you change the code and it still doesn't make sense, and do some more work with it, and it makes some more plots, and the numbers look funny, and you have to keep with it, and checking it out a little bit at a time, and then eventually it'll begin to come together. You're like, oh, okay, this makes sense. I had a coding error here, index number was wrong, let me try that again. Now look at the numbers. Yeah, this kind of makes sense. This kind of makes sense. We've got some weird ones here, but maybe they're just weird. And you go and you look at them, and then so on and so forth. And I think that's the hardest bit, is sort of persistence, but also having the confidence to say, well, let's see if it does make sense, right? If you just say, no one can look at if you're doing original research, it's not like you can look the answer up in a textbook. You can't Google the answer. You have to convince yourself that what you're doing and what the answers are that's coming out of your work makes sense, whether it's theory, whether it's a lab work, whether it's analyzing images or looking at spectra, whatever kind of work you're doing, you've got to look at what you get from your experiment and think, does this make sense? And how do you know whether it makes sense? You can't just ask somebody, does this make, you can talk with somebody and discuss it, But between you, you've got to say, okay, this is the reason why I think it's right. That's tough.
So next question is concerning your choice of the mission. So you were working on the Pluto mission for quite a long time. So what was that made you excited and made you join this mission to explore Pluto in the first place?
So it's a good question. I started off working on Jupiter, biggest planet in the solar system, has a magnetic field, very strong, which fills out a large volume. And the whole magnetosphere, the sphere of influence of that magnetic field, is filled up with material that comes from the volcanic moon Io. And so I was studying material that comes off the moons that becomes trapped in the magnetic field and so on and so forth. Same at Saturn, same at Uranus, same at Neptune. And then along comes Alan Stern and says, let's go to Pluto. And I'm like, Pluto doesn't have a magnetic field, it's too small. Why should I be interested? And he said, maybe Pluto acts a bit like a comet. Maybe Pluto acts a bit like Mars and Venus, and the atmosphere is escaping. Pluto is small, low gravity. Maybe that atmosphere can escape. Quite a lot of that atmosphere can escape, and it would indeed be like a comet. We're going to fly through that with charged particle instruments, SWAP and Pepsi, and measure those charged particles. And so I got interested in the idea that Pluto acts a bit like a comet in that its atmosphere is escaping. And we were going to fly through that. And I got interested in analyzing that. And so I got sucked into the Pluto mission. That's why I got interested.
And there is another question quite similar to this one, but concerning generally your career. So why did you choose to be an astrophysicist, and while studying geophysics in the UK, did you always have an eye on space exploration and particularly American space programs?
So when I was a teenager, I watched every Monday night. There was a BBC program called Horizon, which would be a documentary, science documentary, and there was a lot about geophysics, about understanding the Earth. We were discovering plate tectonics, and I got really interested in that. I was thinking, that's really interesting, and how the magnetic field was involved in measuring the spread of the plates and so on and so forth. At the same time, the US, and at that time the Soviet Union, but predominantly the US, was exploring Mars, exploring the moon, and trying to understand the solar system. And people like Carl Sagan, you've probably heard Carl Sagan on TV movies, he gave these documentary presentations on Mars, exploring Mars, and also future exploration. So I got interested in planets as well. And so there wasn't much of a space program in England. In fact, there was none. So I came over to the US thinking I would stay for a year while I decided what I wanted to work on. And I got sucked into the Voyager mission to Jupiter. And just out of curiosity, just as a little anecdote, when I was a teenager, Carl Sagan came to give a talk, and I went to hear his talk, and I met him afterwards, and I shook his hand, and I was just like, Carl Sagan. And then when I was a graduate student, the first talk that I gave was at a conference, and he was chairing the session, and he put the microphone on around my neck, and I was just like, Carl Sagan, Carl Sagan. So I actually got to meet him, which was a huge pleasure. But I got Voyager, just got me sucked into Voyager, and that was it. I was there for Jupiter, Saturn, Uranus, Neptune.
So I have a question personally. So you're a British citizen, right?
I'm dual American and British. Yes, I became a US citizen 6 days after 9/11.
Yeah.
Not related, but just out of coincidence.
So I was just wondering how you work in NASA if you're not a
Right.
US citizen. Like, how
Well,
does
you can work as a non-US citizen. It helps if you move from a student visa to a green card, a permanent resident. But I became a citizen for two reasons. One, so I could vote, and two, so I could go and work in NASA centers without having to go through huge bureaucratic hassles. But you can, which is a nuisance. But the US, if you work in science, not technology, it's harder in technology. But if you work in science, you can work on a student F visa or a visiting J visa or a visiting H visa before you apply for residency. So 40% of US PhDs go to non-US born people. People come from the outside to get their PhDs in physics in the US. And 40% of the people in this lab that I work in were born outside the US. So there's a lot of non-US researchers here in the United States. Yes, it is possible.
Thank you. So there are a question wondering about if there are any missions planned further than Pluto. So for like I don't know. Yeah.
So
yeah.
I'm laughing because
Charles, something like that. Yeah.
I have a colleague that we were at grad school together, graduate students, and for the past 40 years, he's been pushing for a mission to interstellar probe to go, like the Voyagers, leave the solar system and go out into the interstellar medium with new instruments, not the Voyager instruments, which are kind of on the last legs, to be honest with you. So the interstellar probe mission there's quite a large group of people who were pushing for that. And so watch out, pay attention, because they may, they got a ways to go to get there, but there are people who are pushing to do that. Yeah.
Okay. Should Pluto be considered a planet?
Dwarf people are people. Dwarf planets are planets. Period. Done. Okay?
Yes. Okay. Thank you. Yeah. So this is a question not really related to the presentation, but I also think it's quite important. So considering the time when you work on the Juno mission, so what was the most exciting moment you experienced during that period of time?
So first of all, let me say, it was said in the introduction that Juno was going to end this summer. Nope. We have an extended mission. We've been extended until 2025. So we've currently made 34 orbits of Jupiter, and we're going to go to, we hope, 75. So the mission has been extended and will be more orbits. We've actually shortened the orbit. We just a couple of weeks ago had a flyby of Ganymede. Really cool. Go check that out on the web. Go look at Juno camera and check out the Ganymede pictures. They are really breathtaking. Great. So I'll tell you what my favorite thing is the moon Io is the volcanic moon that dumps out a ton a second of material into the sulfur dioxide, sulfur and sulfur dioxide. It's been known since the 60s to trigger radio emission that we can detect here at Earth. And as it orbits, and we can detect this radio emission. And we flew by with Voyager very close, and we measured the electrical currents that are flowing from Io to Jupiter. And we have been measuring from Earth and with flybys the aurora that is produced. Hubble particularly have shown the aurora in the atmosphere of Jupiter made by those electrical currents with this moon. So if you've got Io orbiting Jupiter, there's electrical currents that flow along the magnetic field and cause aurora at the foot of the flux tubes, the magnetic flux tubes. Now with Juno, we flew right through that magnetic flux tube and we measured the perturbations in the magnetic field, but the electrical currents associated with that. So these are million amp currents, so really strong electrical currents. And we measured the charged particles that are flowing along the magnetic field that generate the aurora. And so that was really cool to actually fly through that very region where the electrical currents and the charged particles are flowing. So that was probably my most exciting moment.
Thank you. So another question is, so what do you think? Do you think there is extraterrestrial life? And do you think there is something out there, probably intelligent, the question is?
Well, the first question is, could there be life out there? There probably very likely is. And the place I would go to look for it, most likely place in my mind, is the ocean on Europa. So that's the second moon, Io, Europa, Ganymede, Callisto, 4 moons, Galilean moons of Jupiter. And so Europa, we've known, has an icy surface. That was from Voyager. Galileo flew by and showed that there's electrical currents that are induced in that ocean underneath the ice. So you need liquid water that's electrically conducting. Ice is not electrically conducting. You need water, liquid water, to be electrically conducting. And we know then that underneath that ice, there is water. And so it's heated by tidal heating, or the same way that Io is so volcanic because of tidal heating of the interior. And so you've likely got relatively warm water with a lot of minerals in there, which would be the perfect place for making life. In the same way, many people believe early life on the Earth formed where there are volcanic vents down deep in the ocean, putting out material, warm material, that it could be the ingredients of life on the Earth. And so are we going to find charismatic megafauna, you know, like whales? I don't know. Maybe, maybe not. But if you want to find some form of life, which would be very interesting to see if it evolved completely different from the Earth, I would say Europa is the most best place to go. Now, is it intelligent? Who knows? Is there intelligent life out some other star system? Maybe. I mean, the astronomers say the probability is very high. Maybe. I think David Grinspoon has pointed out that the biggest problem is that it's unlikely that civilizations survive for very long. Planetary systems don't necessarily live for very long. So having it live long enough to make intelligent, whatever that means, life is a big question. Who knows? Maybe in your lifetime, you guys will get to know.
Thank you. Another question concerning us. So how can we as high school students, and also some of us are international students, how can we contribute to the space exploration today?
Well, the first thing you can do is there are a bunch of online citizen science experiments that have been going on. So JunoCam, for example, on the Juno mission, the data, all the images are made available to the public immediately. They come down. And you can go online, you can download these images, you can play with them, do some science, do some art, explore, and then upload them. And people can look at them. There are thousands and thousands of these images that people have explored, and everybody, it's for everybody in the world to do. There are other citizen science experiments you can do, a lot of astronomical ones where you can download some data, analyze the data, and join in a public citizen science experiment. There are things like counting craters on Mars. There are things like counting stars in galaxies and things like that. So you can do that now. And that's available to anybody, anywhere in the world. Then the next thing that is the most important is to keep up with your math. I'm sure you are all very, I see Dr. Ice putting a thumbs up. I'm sure you are all very competent and capable at math and physics, but stick with it, because you really need that math and physics in order to move forward into the next stage of your career. And so hang in there with math and physics. Probably more important than chemistry and biology. You can catch up with those, but if you get behind in math and physics, it's hard to catch up. And then find a university to go to that has astronomy, planetary science, geophysics, aerospace engineering, electrical engineering. Those are the sorts of topics that you need to get an undergraduate degree in. And you don't need to come to the US as an undergraduate. There are the undergraduate degrees across many countries. Most countries are comparable. It's graduate school that is, if you really want to get into research, then you need to apply either to the US or other spacefaring nation, whether that be China, Germany, India, France, Belgium, and so on, to do and get involved in the space project. Japan, many countries. The United Arab Emirates now has a space program. They sent the Hope spacecraft to Mars. It was built here at the University of Colorado as a training exercise, and now they have their own space program. So there are many ways to get involved. I hope that's useful.
Yeah, thank you. Next question is, how much time more do we have for questions?
I have no idea. Dr. Ice, can you tell us? You're not, there you go.
Yes. So our session is actually scheduled till 2, which is another, about 30 minutes. If she can hold up, which I think she can.
Let me just check my calendar for a second.
Okay, you want to double check?
I can keep going. I would like, how about we go to 10 to 2.
Okay, so lots of time. Okay.
Another half hour. Okay.
All right.
Yeah, okay, then I'll go with the actual questions. So let me find something good. So when New Horizons will run out of fuel, what will happen after that, and what are we planning to achieve before that happens as well?
So fuel is not, okay. With the spacecraft, you're not constantly firing the engines. You only fire the engines when you want to do one of two things. One is if you want to change the direction. So you're going in one direction, change it. You need to fire the engines. The other is if you want to change the orientation of the spacecraft. You have to fire little thrusters. So if you wanted to point your cameras over there, point your cameras over there. Then you have to fire the thrusters. So the only reason we carry fuel is to change either a direction or the pointing. Now, we are designing an extended mission that will have very limited need for those thruster firings. And that is the fuel that will limit our capability to operate as a spacecraft. Because if you can't turn the spacecraft to look back at the Earth and communicate with the Earth, or turn the spacecraft to go take pictures of something, then you can't operate anymore. So what happens after then? Well, it's on an escape trajectory. That is, the speed of the spacecraft is greater than the escape speed to escape the sun, okay, the gravity of the sun. And so it's moving away from the sun, and it'll just keep moving in that direction forever and ever. Slowly slow down, right, but it will keep moving. And we have several spacecraft like that, Pioneer 10 and 11. Eventually Voyager 1 and 2 will go that way, and New Horizons. They will all escape our solar system, but at some point they'll stop communicating because we run out of either ability to control the spacecraft, run out of thruster fuel, or we run out of power. So all of these spacecraft use radioactivity to generate electricity that is used for communication in keeping the spacecraft warm and operating the instruments. And at some point, you run out of radioactivity. Now, the plutonium that they use has a half-life of about 86 years or something like that. So it's quite long, and so the power lasts quite a while. And so I think by limiting the communication and limiting the instruments, you can keep going for a long time. But at some point you do run out of power, and I think power is what runs out before the thruster fuel. It's sort of comparable, probably in the next 10 years. But it keeps going off into nowhere. And eventually, maybe some alien life form will find the spacecraft and wonder, what the heck is this?
And as far as I know, there is also like a message to aliens on the spacecraft. Can you talk about it as well?
Yes, just as Voyager had the record, and I urge you to watch the movie about Voyager. I've forgotten the name of the movie. It's a movie about Voyager. It'll come to me, but I've lost the name. You can go look it up. Watch that because it's quite fun. It came out about 3-4 years ago and talks all about the record. So for New Horizons, we got the signatures. People signed, scratched their name, if you like, on the instrument. So there's that. But we also have some ashes of Clyde Tombaugh that are carried out. But it's not quite like the Voyager record where there was this message from planet Earth. But it'd be interesting to know it would be fun to know what the aliens interpret the spacecraft to mean if they found it. We'll never know.
So you work as an astrophysicist, right?
Planetary scientist or space physicist.
Planetary scientist. Excuse me. Yeah.
It's okay.
So as a planetary,
Astrophysics seems to be they seem to be a rather arrogant bunch of people. So I don't like to use that phrase.
Okay. So as the planetary scientist, what does the regular working day looks like? Yours?
Okay, so I usually get up about 6 o'clock. I go over to my local coffee shop that opens at 6:30. I'm one of the regulars. I've been going there for about 30 years. I walk in. They know me. They know what kind of coffee I like. They make me a coffee. I sit down and I chat with some people, but I also get my laptop out and I do my email and I think, okay, I've got to work on this project today or that project today. And then the Zoom meetings start. You know, with COVID, we've always had telecom meetings, Zoom meetings, but of course now we've had a year of nothing but Zoom meetings, starting to have in-person meetings happening again. But it's been an advantage that you can talk to people around the world, just like we're doing today. So often they are, you know, what's the latest on the Juno mission? Let's have a team meeting to discuss the results that just came in. What do they mean? What do they look like? Sometimes I meet with students and say, how's your data coming along? And they show me their data and we look at it and we say, does this make sense? And I'm like, maybe you've got a coding error. Let's see if you plot this out. What does it look like? What if you change this? What happens? Does this make sense? Does this make sense? This sort of thing. There is some, you know, the lab, we get together and talk about, have seminars 2-3 times a week. I have listen to a seminar from somebody from around the world. Because of COVID, we've had seminars from people all over the world. But before COVID and maybe after, we'll mostly have people who just are passing through town. Today, I've got to get my poster ready for a conference we're having in a couple of weeks. I've got to write about the environment around Ganymede. I've been working on Ganymede and thinking about Ganymede for 2 reasons. One is Juno just flew by Ganymede and we made some measurements. Ganymede has its own magnetic field. So it's a magnetosphere within the magnetosphere. And so we're working on what the environment is like. And I've got a poster that I'm putting together with a bunch of plots showing what the environment is around Ganymede. So how much does it vary? And how much might we expect that interaction to vary? So I have to get that ready because our conference is in a couple of weeks. And then also I have to review a paper for a journal. I have to look at it and say, this is good. Could you explain that? You got a mistake here, whatever it is, that sort of thing. So those are the sort of things we do during the day. Make presentations via Zoom or in person nowadays, come back to in person. I don't write code anymore. I used to. I did Fortran and IDL and Excel, and there's MATLAB and Python and Mathematica, and everybody has their own favorites. But I get the students to write the code and I look at the plots that they produce and we discuss them. What else do we do? Oh, I'm also involved in planning new missions. So we have this decadal survey that's going on, and I'm on the Giant Planets panel, and we're trying to make the case to go back to Uranus and Neptune. So I have to meet with my colleagues, and some of them are like, no, let's go and look at the rings of Saturn. No, let's go and look at something else. And I'm like, no, Uranus and Neptune, you know. So we have to make the case to go for the next mission. So, well, I have a meeting this Friday, and because it's around the globe, we've got people from around the globe, it's going to be very early in the morning. So, but luckily I'll go around to my coffee shop, get a cup of coffee, and then jump onto the Zoom.
Yeah, and sorry, connecting to your work, I think you work a lot of time. And how do you manage not to burn out? And if you had those moments, how did you deal with them?
Right. Yeah, I had a long day. Yeah, was it yesterday or the day before? And I was burnt out from zooming. And my husband said, we've got all these branches in the backyard. Could you put them into the waste bin? I had to chop them up to fit them into the waste bin. And that was a perfect, he knew that I needed a mechanical job that didn't take brain work, that, you know, maybe I could listen to a comedy show on my headphones while I was chopping up wood and putting it into a bin, you know, that sort of thing. You have to find other jobs, right? Emptying the dishwasher, doing other things. I also, you know, I go for hikes. I love to go hiking. Here in Boulder, we have lovely mountains, and I'm lucky enough to go for hikes. He and I go rock climbing in the weekends too. So that's really good because you have to focus. You can't get distracted and be thinking about your work while you're on the rock. So that actually is an excellent way of really getting away from work. So you got to find other hobbies, you know.
Yeah, next question, more like a short clarification. You name a movie, you referred to a movie recently. What was the name again? The Furthest?
It is The Farthest. Yes, thank you. I knew one of you would Google it and find it. Excellent. The Farthest, yes. It's made by an Irish woman, and it's about the history of voyages. She got some lovely shots. I would have liked a bit more science, a little less artsy-fartsy, but it is fun, and it's all about, and the record is really beautifully done. It's a good movie. It's a good movie. I recommend it.
Yeah. So in what ways do you imagine spacecrafts will be optimized, improved in the future missions?
They'll be smaller and lighter. And that's really big because the hardest thing, there are three difficult things with space missions, okay? One is propulsion. And for propulsion, mass it's actually a nonlinear phenomenon, right? And when they say this is rocket science, it's because you've got to propel things into space and through space. And you need to have an efficient mechanism of propelling things. So propulsion is one of the key things. And so finding an effective way to do that is very important. And you have to carry the fuel, which is mass. So you can see how it's a nonlinear problem. The more fuel you carry, the heavier the object, the more fuel you need to propel it. And so that being efficient is key. The second one is power. You've got to power your spacecraft to do things. Now, what's interesting is modern equipment needs less and less power. And you think about how increasingly everything is running on little batteries, right? Tiny little batteries. You need very little power these days to do things. Things are becoming much more efficient in terms of power. So I think that's getting better, and we're learning ways. The problem is you can use solar power when you're within, say, the distance of Jupiter. But once you get beyond Jupiter, the solar power, just because of 1/r² drop off in the solar flux going out, sunlight going out, it just gets so much harder as you go out, right? 1/r², just you just think of the area of a sphere, right? Goes as 1/r². And so if you move out beyond Jupiter-ish, even with efficient solar panels, it's really hard to work. And so you've got to find some other power source. And radioisotope thermoelectric generators, or RTGs, is what we've been using in the past, and they're pretty efficient, but they do require very careful technology, And yes, radioisotopes are nasty to humans. So making the radioactivity they produce can be very damaging to humans. So you have to be very careful how you use them and make them. But we could do better maybe with finding better ways to do power. But the advantage, what's good about new technology is you develop things that need less power, right? So we're getting more efficient in our use of power. The third of those three is communication. And you absolutely need to be able to get the data back, right? So somebody had this idea of sending some tiny little spacecraft out into the outer solar system to the next Alpha Centauri. Let's go to Alpha Centauri with a little thing, right? It's a matchbox or something. Well, okay, that's a great idea, but you can get it out there maybe, but how are you going to get the information back? And what's the point of going there if you're not going to bring the information back? You have to carry a radio antenna to send the information back. Or even if you do fancy laser communication, you got to carry a laser to send the information back. And that requires some clever mechanism of communicating over a long distance. So those are the three biggies, right? To think about propulsion, power, and communication. And what are the ways in which we can make those more efficient? And smaller spacecraft are easier to propel. We need less power these days, but you do need to communicate. Now, I think the way to solve the communication problem, one way to help with the communication problem, is to make bigger ears on the ground. So instead of having one or two, we actually have three main radio facilities around the globe of the Deep Space Network. One in Australia, one in California, and one in Madrid. Why don't we have more and bigger antennas, arrayed, multiple arrays, like the very large arrays in New Mexico or in South America, or even in, I think in the Ukraine. But we need to do more ears on the ground to be able to listen and get weaker signals from further away. That would be the way, partly the way to solve the communication problem. So there are technologies that will make a big difference, but focusing on those three biggies are the ways to do it: power, communication, and propulsion.
Yeah, I'm actually from Ukraine. That's nice to hear. So next question is concerning artificial intelligence and communication. So how can we use potentially artificial intelligence to decrease the communication delay, the satellites, and generally the use of artificial intelligence?
I'm not sure you can change the delay, because, you know, speed of light, the speed of light is the speed of light, is the speed of light. I mean, that's the speed of light. You ain't going to change that. Okay. So, but what we can do, and people are beginning to do, is onboard data processing. And I think that's where AI comes in. Whether you call it AI or something else doesn't, you know, call it what you want. The point is, what we're going to be doing is analyzing the data on board, so we don't need to send as much down. So say you're flying through the solar wind and you want to measure the solar wind, and you can make measurements and analyze the data and average them, or take samples. And then what you do is you analyze the data, you're going along and you autonomously analyze the data, and then the spacecraft goes through a period where there's a lot of turbulence or a lot of activity, okay? And then it dies down again. And so what you would do is you'd have to do onboard data processing that analyzes the data and realizes the time when it gets very active and then dies down again. And what you would send back to the Earth would be, here's the sample here, wait a while, sample here, wait a while, sample here, sample here, sample there. And along with that sample, you would have a thing would say, pretty boring, nothing much happening, pretty boring, nothing much happening, pretty boring, nothing much happening. Very exciting, there's some stuff here. We've stored the data on board. You might want to download it later. Okay. And then the humans on the Earth would say, yeah, let's get that exciting data. You'd tell the spacecraft, yeah, send that down, please. Okay. So that sort of thing, you could use onboard autonomous processing of the data to limit the amount of stuff you need to communicate. So that's addressing one of those three, the communication problem. So you're working with the spacecraft as a robot. So you're working with it and saying, you know, I want you to do this, and tell me what you're finding.
Thank you. Next question is asking about the mission proposal. So how long does the whole process of proposing the mission and getting it approved take usually? And generally, how often do you propose a new mission?
This is a great question. And I'm looking around my office because, just hang on a second. Let me see, what do I have? Oh, dearie me. Let me see. Wait a minute. Yes. I have it here. The New Horizons mission to Pluto proposal. You see how fast it is? Okay, that was just the main bit. It's, how many pages is it? It's got 8 appendices, 123 pages. Okay. Now, this was just the main bit of the proposal. And once we got selected, we had to, I'm sure there was much more paperwork, but and that probably took, well, as I told you, we had 4 studies that were done before this final proposal went in. And so this probably took about a year, 6 months to a year. I mean, not solid working on it. You just do it while you're working on other stuff too. And I've done this was the first in the New Frontiers scale. So New Frontiers are about $1 billion, okay? That's what it costs to do a mission to the outer solar system. So Juno was the second New Frontiers mission. And $1 billion is, you can do the math, it's a cafe latte per taxpayer in the United States. So there's about 300 million people, 330 million people in the US. And you divide $1 billion by that, it's about $3. And that's what it costs to get a fancy cup of coffee. So I think it's well worth it per taxpayer. And we have to write these proposals, they get reviewed. There were probably about 4 at the time, each time, for these really big proposals, maybe 5 or so. For the smaller proposals, you may be competing with 20 other people, but these big ones, there's only a small group of people proposing to do, and there's very limited targets to do these proposals. So that's the sort of effort that's involved. And you know, it's mostly, what have we got here? Words, but there are some sort of, you know, spacecraft diagrams and tables and things like that. Okay, fold out. What else have we got? Oh, here's oh, look at this. There's all sorts of details of the different instruments. So, you know, quite detailed information with numbers saying this is the size, this is the power, this is the cost, this is what's involved. And then, you know, it's really quite a big, complicated paperwork involved. And it says this is the plan, this is how we're going to do it, and so on. Yeah.
The last small question So what do you think about the heart on the Pluto?
Oh, I was fortunate, right? Wasn't that a piece of good luck? I mean, when you look at it carefully, I guess it's kind of sort of a heart, but you know, I think I don't know. I'm not a very romantic, soppy person, to be honest with you. You know, but why not? I mean, it could be a lot worse, right? It could have been something else. I like the snowman, though.
Thank you so much for answering the questions.
Sure.
That's interesting.
Yes. Thank you so much for your time to give us this presentation and answer our questions. We really, really, really appreciate it. I'll speak on behalf of
Pleasure.
participants. So at this time, you are dismissed. There were a few things that she mentioned you might could follow up on, a couple of websites, obviously a movie if you haven't seen that. So there are some interesting things for you to do to follow up this presentation. And we'll see you in Work Play Block later today.
Okay, thank you very much. I've done this SSP a few times, and it's always great. I love you, great guys.
Thank you so much.
Come to the University of Colorado and to do your PhD.
There you go. There you go.
Okay. Bye.
Thank you. Bye.
Thank you.